Okay, I think it's recording. Yeah. Okay. So, welcome to lecture 3 of randomized algorithms. So, last time, so in the last week, we saw what randomized algorithms are, and we also saw two variants, Las Vegas and Monte Carlo algorithms, and we saw quite a bit of probability theory. And what we'll do what we'll do today is we'll first see an equivalence between Las Vegas and Monte Carlo algorithms. And then, so actually, we were supposed to do this last week, but yeah, we were able to cover this last week. So we'll cover this today, and then after we have done this, we'll look at randomized quicksort. Okay. So yeah, whenever I upload these notes, you would see this happening that some of the things that I've written under the head lecture 2 might be covered in lecture 3. Yeah, these would keep on happening. Okay. Yeah. So let's quickly recall what Las Vegas algorithms were and what Monte Carlo algorithms were. Okay, so what was the Las Vegas algorithm?
So during there was a chance of in the Las Vegas there was no chance of making error, and in the
Right.
Monte Carlo we can have some error can be tolerated with some probability of less than or equals to 1/3.
Yes. So a Las Vegas algorithm always outputs the correct answer, but there was some drawback to it, right?
Yes, yes. So but then it may take quite a long time. That is,
Right. So what guarantee did we have on its running time?
so I mean running time could be exponential. I think.
Right. But its expected running time would be polynomial, right?
Yes, yes. So
Yes.
it's just a common characteristic of all the randomized algorithms that sometimes they may take exponential time, but then expected value would may come out to be polynomial.
Right. On the other hand, Monte Carlo algorithms might output wrong answer with probability at most 1/3, and there is nothing special about 1/3. We'll see that today. But for every random choice, there they would halt in polytime.
Yes, yes, yes.
Right. So
And
regardless of the random choice, they would halt in polytime. So there does
yes,
not exist any random string for which they would run in say exponential time. Right.
yes, yes, yes.
Yes. So this is a difference between Monte Carlo and Las Vegas algorithms. Okay. Yeah. So now let's so first we'll see how to convert a Las Vegas algorithm to a Monte Carlo algorithm. Okay. So the theorem will prove is this. Let A be a polynomial time Las Vegas algorithm for a problem P. Then P also admits a polynomial time Monte Carlo algorithm okay. So given A, we want to create another algorithm A prime, which is Monte Carlo. So is the goal clear?
Yes. In
Yeah.
case you're writing something here, then that is not visible. Did you
Okay.
write something here that a prime you want to convert a into the
No,
a
no, no, I
prime?
haven't written anything yet.
That is okay.
Yeah. Okay. So okay, now I'll start writing. So this is the wrong color. This seems to be the right color. Okay, yeah. So yeah, so this is the goal. Okay. Now A prime can run for the running time of A is x is okay. The expected running time of A is polynomial, but for some random choices, it can run for a very long time, right?
So, yes.
So what's one very natural way to ensure that for every random string, A would run in polytime? Well, like what's the dumbest thing to do?
Yes. So yeah. I don't know how can this be done.
Okay, so let Olsen. Okay, 4 times Tn. Yeah, we might need to change the constant 4. Okay, so this is what we are going to do. So now can you guess what we'll do?
So I think that whenever a random string is going to take the expected amount of the time, that will be considered as an error in the corresponding Monte Carlo.
Yes, sort of. So not expected time, 4 times the expected time. And we'll see why we need 4 over here.
Okay. Okay.
Yeah. So here's what A prime looks like. Uh, out, outputs a value, return that, or outputs a solution, let me say. Return that solution. Otherwise, return any arbitrary solution. Yeah, so this is what A prime is going to do, and it's pretty clear that the running time of A prime is 4Tn, right?
Yes.
Yeah, so it's clear that now the question is, so okay, so is A okay, so from what I've written till now, uh, have we proved that A prime is a Monte Carlo algorithm?
No.
Yeah,
And
so what is missing?
moreover, I'm not clear that how can this happen that the algorithm A, after running it, say for 4 p.m. steps, it does not generate the solution. How can this happen?
Okay, so the expected running time, okay, the only guarantee that we have on the running time of A is that it's in expectation, it's Tn, right?
Yes.
But it's possible that for just one random string, it runs for time 2 to the n.
Mm-hmm. Mm-hmm.
So we saw this example last time, right? That for like just for one random string, the value of a function is 2 to the n. For every other random string, it's n.
Yes.
Then in expectation, it would be something very close to n, right?
Yes.
I
Uh,
think, did I erase it? Yeah, maybe I erased that.
no, it is there. It is there.
Okay, okay. Yeah, so then it's fine. Yeah. So it's possible that after running for 4Tn time steps, A might not have outputted a solution, right?
But how can this happen that the A might not have generated the solution? A is supposed to generate the solution every time. It may take some long time, but it would be generating the solution.
Right, right. So what I'm saying is run A only for 4Tn time steps. So don't
Oh,
let A run forever. After 4Tn time steps, stop it forcibly.
okay. Okay.
So
Yes.
that's what the first sentence is, right? Run A for 4Tn time steps.
Yes. Yes.
Yeah, not more than that.
Yes.
Yes. Okay. So now the running time of A prime is 4Tn, right?
Yes, but then I do not understand the reason behind this 4, that why are we running it, say,
Yeah.
4 times and not any other number?
Yeah, okay. So far we have just showed, okay, 4Tn equals poly n. Let me write that. Okay, so Monte Carlo algorithm has two conditions: polynomial running time that we have taken care of. The other condition is the error probability, right?
Yes.
Right. It's less than or equals to. Okay, so is this claim fine?
This is okay. This is
Yeah, because if A had halted in 14 time steps, then
Mhm.
it would have whenever it halts, it returns the right solution, and A prime would have returned the same solution, right?
Yes.
Yeah. So now we need to upper bound this probability. Okay. Okay, so what is this? Let the running time of A and this quantity. So the thing on the RHS is less than or equal to probability that X is strictly greater than 4Tn, right?
Yes. And why so? Because if let x be the random variable representing the running time of E, so if the value of x is greater than 4n, so some errors would be there. Uh,
No, no,
uh,
so if X is greater than 4n, that means that A ran for time more than 4n, right?
yes, yes.
So these two statements, okay, where is my highlighter over here? So these two statements are equivalent. That's what I'm saying.
Yes, yes, but then this less than or equals to is not that much clear. That how is that possible that a prime is making an error would be less than? I think that a prime is making an error is equal to
No, no,
that.
no. It comes from here. So you are generating it. If A prime, if A doesn't hold, you are generating an arbitrary solution, right? But you might get lucky, and that arbitrary solution is actually the correct solution.
Oh yes,
Yeah. So that's why you need a less than equals to over here.
yes,
Yeah. Okay. So my claim is this is less than or equal. Okay. Let me write one more step now. Okay. Let me do it like this. So this. Okay. First of all, x is okay. X is a non-negative random variable which takes integer values, right? Running time cannot be negative,
yes,
which means I can use Markov's inequality,
yes, yes.
right? So what does Markov's inequality say?
So
Probability x is greater than equals to c is at most
expected value of x and divided by c.
c over here is 4Tn, right?
Yes,
Okay, and this is just Tn over 4Tn. Why? Because x is the random variable representing the running time, and the expected running time, i.e. expected value of x, is Tn.
Yes.
And this is just 1/4. Yeah, so the probability that A prime makes an error is at most 1/4, right?
Yes.
Yeah.
So I think that we could have, instead of the 4 TN, we could have run it say for 3 TN time, and then it will
Yeah,
match.
3 TM would have also worked.
Yes.
Yeah. So is this fine?
Yes, yes, perfectly.
Okay, so we have seen how to convert a Las Vegas algorithm to a Monte Carlo algorithm. Now, before we see how to convert a Monte Carlo algorithm to a Las Vegas algorithm, we need to look at one more distribution, which I forgot last week, and that's a geometric distribution. So we say that a variable x is distributed geometrically with a parameter p if x takes values 1, 2, 3, and so on, so positive integers, and the probability that x is k is equal to 1 minus p to the k minus 1 times p. And the expected value of x would be 1/p, and its variance is 1 minus p times over p square. Okay.
Yes. Yes.
Now here's an interpretation of the this random variable. So let's say p was okay. Okay, let me not fix p. Okay. So x is the number of times we need to sample from the Bernoulli distribution with parameter p till we get a 1.
Mm-hmm. Mm-hmm.
Okay. So when is x e okay, when is x equals to, okay, what is x equals to 1? This would disappear, right?
Yes.
So what x equals 1 is p. So if I were to toss if I were to toss a p bias coin once, I would get heads, i.e. 1, with probability p, right?
Yes. So basically,
Right.
what is happening here, that we are flipping a coin, say k number of the times, and in the hope of getting one success. So we are getting the first success after k unsuccessful attempts.
K minus 1.
Is this like this?
Yeah. So it's essentially that. You just missed one detail. It's k minus 1 instead of k. So what's happening is this. X equals k corresponds to the event that you tossed a coin k times. The first k minus 1 times you got tails, i.e. 0, and the kth time you got heads, i.e. 1.
Yes. Yes.
Yeah. Yeah. So like you said, it was k failures, right? It's k minus 1 failures.
Yes.
Yeah.
Yes.
Yeah. But I think sometimes the geometric random variable is also defined with k failures. So sometimes probability x equals to k would be k over here.
Okay. Okay.
It depends on the source. Yeah.
All right.
Yeah. But the like interpretation is it's the number of times you need to toss a coin to get a success. Yeah. Okay. So now let's look at the second theorem. And okay, so now we want to convert a Monte Carlo algorithm to a Las Vegas algorithm. Okay. So let P be a problem such that a supposed solution of P. So given a supposed solution of P, we can verify whether it is correct or not in polynomial time. Okay. Then if P has a Monte Carlo algorithm, it also has a polynomial time Las Vegas algorithm. So is the statement clear? We are requiring P to have one extra condition, that its solution is efficiently verifiable.
Yes.
Yeah.
Yes.
Okay. So now let's see. Okay, I would need an extra page maybe, but I could cover it later. Okay, so let's see a proof for this. So we will create the Las Vegas algorithm. Okay, what's the expected running time? Okay. Last week is I'll go A prime. Yeah. Okay, so this is what we are going to do. Okay.
Yes.
Actually, not 3TN. Yeah, slightly more. To verify the solution. Okay, so now that I have written this down, like, would you like to guess how we would do this?
Yes, so we would be running Monte Carlo algorithm till we find an error. And say we are getting the error in the after say kth here.
Mhm.
So then this k thing can vary. I mean, then we will be computing say this the average value of k thing kind of a thing. So that because for the Las Vegas we need to find the solution, and I guess that
Yes,
average value of this k would come out to be may come out to be the polynomial kind of.
right. Yeah, so what we'll do is this. Uh, A, A prime looks like this. Hmm. Yeah, how do I want to write this? While, yeah. Hmm. Yeah, so this is the proposed algorithm. So what this is doing is it's running A, and whenever A halts, okay, A would always halt in time Tn and output a solution, right? So the solution might be wrong, but it would output something when it halts, right?
Yes, yes, yes.
All we'll do is verify that if it's correct, we are done. If it's not correct, we repeat.
Yes. This
Okay.
is easy than expected. Yeah.
Yeah. Okay. So to get a correct solution. Yeah. So x is a random variable which represents the number of time we need to run A, i.e., the number of times we need to run A till it outputs a correct solution, right?
Yes.
Yes. Okay, then what's probability x equals 1?
So, so the probability is that we have got failure, say for some time. Say we got failure. Say so we run. Say this step number two, say k number of the times. No, no, step number three, say k number of the times. So then it shows that we got I mean those many failures, and then finally we got the solution. So we take the help of the geometric distribution here.
Yeah. So what's probability x equals 1? It's 1 over 3, right?
One
Because
over.
a, oh, wait. A, or is it probably 1 over 3? So this is 2 over 3.
Yes.
So the probability that it does not make a mistake is 2 over 3, right?
Yes.
Right. So what's probability x equals 2? So this means in the first iteration it made an error. In the second iteration it didn't, right? In general, probability x equals k. So the probability is uh, so the p is 2 over 3, right?
So, what does it mean that A errors with the probability of 1 by 3? Did you mention this thing anywhere earlier?
Okay, so what's the definition of a Monte Carlo algorithm? Okay, where is it?
Oh, I see. Because of
Yeah,
that thing, that
yeah.
inequality, the error originated by less than or equals to 1 by 3.
Yeah, so it produces incorrect output is at most one third.
Okay, okay.
Right. Yeah, so x is distributed geometrically with this. So expected value of x
Is equal
is
to
3
K,
over 2, right?
1 by P.
Yeah, so that's 3 over 2, right?
Yes, yes, yes.
Yeah. Therefore, expected because every time I run A, I need to do two things: run A and verify the solution. This is the time required to run A. This is the time required to verify the solution.
Yes.
Right. So this is the this is the expected running time of A prime. Sorry, A prime. Is this fine?
Yes.
Yeah.
Uh, yes, this is fine.
Again,
Yeah.
I overestimate. This could have been 3 over 2.
Yes.
Yeah.
But my question is that what is the intuition behind this interconversion of Monte Carlo and Las Vegas? What benefit
Okay.
exactly this conversion brings to us?
Okay. So let me first talk about this first conversion. So over here, you have something that never makes a mistake, right?
Yes.
But takes too much time. So
Mm.
like the most naive thing to do is, okay, let it run for some time, hope that it outputs a solution. If it does, good. Otherwise, like it has taken too much time. This needs to stop.
Mm. Mm.
Right. That's the intuition over here. And
Mm.
to formalize the intuition, you need this Markov's inequality.
Yes.
Yeah. And for like from Monte Carlo to Las Vegas, it's this. Okay, you have something that might succeed, but it might also fail, right?
Yes.
So run it till it succeeds. That's the only thing you can do, right? There is
Yes.
no other way to guarantee success. Okay, it's basically, what's that saying? Try till you succeed. Something like that, right?
Yes. Yes.
So that's the only thing you can do. You can try till you get an answer, right? Till you get a correct answer.
Yes. Yes. So probably the proverb is that you fake it till you make it.
Oh, can you repeat it?
Uh, you fake it till you make it.
Oh, okay. Okay, yeah, that's the one. Right. Yeah, so that's what you need to do to convert a Monte Carlo algorithm to a Las Vegas algorithm. And for Las Vegas, it's like, okay, there is this thing that would always work, but would can take a very long time. So what's the only way to ensure that it won't take a long time? Stop it after that time, right? Forcibly.
Yes. Yes.
Right. And that's the only thing that we did, right?
Yes.
Yeah, so sort of in both the cases, there was only one thing you could do. That's what we did, and then we used probability theory to argue that that would work.
Mhm. Mhm.
Yeah. Okay, so is this fine? Okay, then let's move on to boosting the success probability of the Monte Carlo algorithm, right? Okay, so we defined a Monte Carlo algorithm to be an algorithm that makes error with probability at most 1 over 3. But there is nothing special about 1 over 3. In particular, it could have been 1 over poly n for any polynomial function. Okay, and that's what
Yes.
we'll see over here. Now, there are ways to boost the success probability of the Monte Carlo algorithm for like search problems, optimization problems as well. But for the sake of simplicity, we'll just focus on decision problems. Okay.
Mhm.
So a problem P is said to be a decision problem if for every input X, the correct answer lies in yes, no, or 0, 1.
Yes.
Yeah, so decision problems sort of correspond to languages in complexity theory,
Yes.
right? And we will denote the correct answer by P of X. So if the correct answer is, oh, I wrote yes, no, I should write 1, 0 over here. Yeah, because yes means 1, no means 0. Yeah, so if the answer is yes, the output P of X would be 1. If the answer is no, the P of X would be 0. Okay.
Yes.
An example of a decision problem is, does a given natural number have a prime factor between A and B? The answer is either yes or no.
Yes.
Yeah. And for decision problems, we can further classify Monte Carlo algorithms into two types, one-sided error and two-sided error.
Yes.
Yeah, so an algo is set to a one-sided error if it is always correct when Px equals 0 or Px equals 1, but can make an error if Px equals 1 or Px equals 0. That is, if the correct solution is 0, it would never make a mistake. But if the correct solution is 1, it might make a mistake. Okay.
Yes.
So formally, if Px equals 1, then the probability that Ax equals 1, i.e. A does not make a mistake, is at least 2/3,
Mhm.
i.e. A makes a mistake is at most 1/3, right? Because
Yes.
this is the same thing as saying probability Ax is equal to 0 is at most 1/3.
Yes.
Yeah. And if Px equals 0, then probability that Ax equals 1 is 0. That is probability Ax equals 0 is 1. That is, it does not make mistake with already 1.
Right.
Right. And for two-sided error, the algo can make a mistake when Px equals to 0 as well as when Px equals 1. Okay. And formally, this means that Ax equals Px is at least 2/3, i.e. it does not make a mistake with probably 2/3.
Yes.
Right. So first, let's see how to, yeah. Were you saying something?
No, so I guess that I mean this is analogous or similar to the randomized polynomial plus RP and then BPP kind of thing.
Yeah. So,
Studying the complexity field.
yeah. Okay. RP does not make a mistake. Yeah. Okay. I
So
think what
RP
I've
make
written over here is RP.
RP makes one side mistake and then BPP two sides mistake.
Yeah, but
And
okay, so there are two things, that RP and co-RP. So what I was wondering is, the thing that I've written over here, is it RP or co-RP?
yes, so since here all the strings which are the part of the language will get accepted with the probability of two-third, and the
Okay,
strings
this
which
is
are
RP.
not the part of the language are definitely going to be removed. So
Right.
this is
Yeah, this is RP, and if this were zero, this were yeah. So if this were switched, then this would be co-RP, right?
yes, yes. If I switch
Yeah,
it,
and this is BPP. Yeah, you are
this is
right. Yeah. Okay, so now let's look at how we would boost the success probability with for one-sided array algorithms. Okay. Yeah. So what's okay? What do you do over here? Yeah. Okay. So what would you do to boost the success probability of A? What's the most natural thing to do?
so we repeat the experiments multiple times.
Yes. So define A prime as follows. So we'll K is a parameter. We'll fix it later. Okay. Okay. So I'll run A, but then what? Should I run it for K times? And if I run it for K times, what should I output?
Uh, okay, so uh,
Okay, so okay, before that, let me assume that I'm in this case. That whenever A outputs 0, it's always correct.
yes. So say if okay, so when it so okay, so for x is equal to zero, even if I run it say for k times, the value would remain as zero. However, for the
Right.
previous case, when the probability is two-third, so that will become pretty low, say two by two-third raised to the power k kind of it. So then basically we are improving. So we are improving what? So one value will become two by third raised to the power k. The other value will remain
Yeah,
as
okay,
zero.
so let's not worry about the probabilities. Let's just worry about what should the algorithm do. So algorithm would run A, okay. But then
Yes.
it also needs to output something, right?
Yes.
So my question is, what would it output?
So uh, output would be one. Output would be zero. I'm for pretty sure that the output is going to be zero. If so, I cannot understand this question actually.
Okay,
Uh,
so can you see
because
my screen?
because I
Or
yes, your screen is not visible. I
uh,
mean to say that uh, for all the strings which are the part of the language are getting accepted with that.
yeah, so let me disconnect and rejoin. Okay, let me try to share screen like this. Okay, now you can see my screen, right?
Yes, yes.
Okay, so okay, let me write down and then I'll see. Okay, so run A. Rather, let me do it like this. Okay. Okay, so we would run a k times, but if in any one of those k iterations it outputs 1, we output 1 and halt. Okay.
Yes, yes.
Otherwise, we continue.
Right, right.
And if we did not, so if we exited this loop, which means we never outputted a never outputted 1, and so a prime never outputted 1 and halted, which means all of the a's outputs were 0, right?
Yes,
In
yes.
this case, output 0.
Yes, yes.
Okay. So now let's look at two cases. Okay. First of all, what's the running time of a?
So running time of E was Tn.
Is
A
less
prime
than
of A prime is
k times tn, right? Okay. Now about the error probability. So probability that yeah. So when px is 0, what is the probability that a prime would output 1?
So, yeah, so this probability would be, say, 2/3 raised to the power k.
No, 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 no.
Why so? The
Okay.
probability that
When
A
does
prime,
a prime output 1? A prime output once if and only if
yes, some run of A resulted into 1.
outputs 1, right?
Yes.
But this
And
probability is 0. Why? Because look at this. So we were in this case, right? If px equals 0, then ax never outputs 1,
oh, yes. So these are
right?
the notations actually. So if Px is equal to 0 means if Px is equal to 1, then this is the correct output. And then, yeah, so now understood.
Yeah.
Yes.
So basically, when px equals 0, a never makes a mistake. So a always outputs the correct thing, 0, which means a never outputs 1,
Yes. Yes.
right? Okay, now this part that you were talking about, probability. Oh, yeah. We'll let this fall.
Yes. So that Px is equal to 1. And the probability of uh, A prime x is equal to 0
Okay, yeah, let's do 0.
is equal to probability that some runs of the output A, all runs of A outputs A.
Output 0, right? Because even if one run outputted 1, we would have outputted 1 and halted,
Yes.
right? So, okay, I need to change the specification slightly. Yeah, these have to be independent. Yeah, so it's the intersection that the ith run outputs 0, right?
Yes.
But all runs are independent. So this is equal to is this fine?
Yes. Yes.
Okay, now what's the probability that the ith run would output 0?
So can you show the notations again? That used to be 1 by 3.
Yes.
So 1/3 raised to the power k and then multiplied by
Nothing,
1/3.
right? This is it.
Yes, yes, yes.
Yeah. Let me add a page. Okay, so for k equals n, running time is let me write the formal statement. Yeah. So this is what we have achieved, right? A polytime algorithm with exponentially small one-sided error, right? Am I audible?
Oh, I was on mute. Yes, yes,
Oh
it's
yeah, yeah.
correct.
Oh yeah,
It's
yeah.
yeah.
So this is fine, right?
Yes.
Okay, so over here, like before we move on to two-sided error, re- observe that over here we crucially use the fact that the algorithm is one-sided error. Why? Because okay, what do we know? We know that okay, okay, when does the algorithm output one? Only when px equals one, right?
Yes.
However, the algorithm might output zero when px equals one. That is, when the algorithm outputs zero, you cannot be sure that it's correct. But whenever it outputs one, you know for sure that the algorithm is correct,
Yes.
right?
Yes.
And this we crucially use this property to halt and then decide what to output, right?
Yes.
So the one-sided error nature of A allowed us to decide the output having seen k outputs, right? Of the k runs.
Yes.
Okay. Now we'll move on to two-sided error and we'll see that this is no longer the case, right? Because in two-sided error, you can make a mistake when you output zero. You can make a mistake when you output one. So you have a bunch of zeros and ones. What do you output now?
Yes. Yes.
Right. Okay. So the boosting the success probably of two-sided error, right? So mm, Tn. So here's I will define A prime. Yeah. So okay. If you want to boost the success probability, there is nothing else you can do other than running multiple times, right? So that
Yes.
remains the same. Mm. Yeah. Okay, so what we are doing is the following. We are running a k times independently, and we are calling the output of the ith run xi. Then, if at least k of the two xi's are 1, we output 1, else we output 0. I.e., if the majority of xi's are 1, we output 1, otherwise 0, right? So we basically output the majority of xi's, right?
And yes, but then, I mean, in the two-sided errors, the
Hmm.
probability of the AX is equal to PX was greater than or equals to two-thirds.
Right.
So it shows that if in true, if the values are 1, then we would be getting, say, more than two-third number of the ones should be 1, in fact. And
Approximately, yes. Yeah,
yes, and
so right now uh, I've written k over 2, but like we might like to get like when we do the analysis, we might change this constant. Okay.
okay, okay,
Yeah.
yes,
Okay. So first, let's just look at the running time of A. So what's the running time of A prime?
KT.
Yeah. Okay. Now about the error probability. So
So it was two-thirds, so it's
let us
not equal to this.
okay. Do I want to do this but in the general case or just in the case when px equals 1 and then say that the other case is similar? That would be easier.
Yes.
Yeah, because everything would be flipped essentially. Yeah. Okay. So A prime x is not 1 when at most k over 2 minus 1 of the x's were 1, right? Which
Yes.
means is this fine?
Yes, so a prime x is not equals to 1 if the probability of the summation of all the xi's is less than or equals to the k by 2. This is correct.
Yeah. Okay. So
So n dot expected value of x1, and that is n dot the expected value of x1 was 1 by 2 by 3.
yeah, because it okay. So here px is 1. So it output. So the probability of outputting the correct answer, which is 1, is 2 over 3, right?
Yes,
Sorry, not this.
yes, yes, less than or equals to.
Yeah. Okay. So now okay. So what was Chernoff-Bo's found probability that I'll just use one of it. X is less than or equals to
e raised to the power minus delta square. Expected value of x minus 3.
Yes, right.
It was 3, I guess, or 2. I don't remember correctly.
Oh, so exp is the exp to the something, just means e to the something.
Yes, yes. And then
Yeah.
in the denominator, it was 3 or 2.
Oh, so I think 3 was in this case. Yeah, but let's check. Yeah, 3 was in the other case.
Okay.
Yeah. Okay. So now over here, what do I want? I want to upper bound. Oh, what am I doing? I didn't run it for n times, right? I ran it for k times. So this should be k times, right? Yeah, I want an upper bound on this. Okay, so we need to equate k over 2 and expected value is. So, okay, so to apply the Chernoff bound, we need a value of delta, right?
Yes.
So yeah, to obtain an appropriate value of delta such that this value becomes the value we are interested in, k over 2, we need to do this. So therefore, k cancels out. 3 over 4 is 1 minus delta. This is fine. K cancels out. 3 over 4. Yeah, this is fine, right?
Yes. Yes.
Yeah. So therefore, probability that okay, so delta is 1 over 4. So 1 minus delta is 3 over 4 times expected value of x is the value we were interested in is upper bounded by what do you get from Chernoff's bound? Exp minus, okay, so delta square is 1 over 16 times the times 1 over 2 times the expected value of x is k times 2 over 3. Okay, 2 cancel out. K over 48.
Yes.
Right. Yeah. So, okay, the case when yeah, one way to do this would be to instead of okay, instead of looking at x size, look at y i's which are 1 minus x size.
Yes. Yes.
Right. Because in that case, you'll be outputting measured 0 when majority of yi are 0.
Right. So I
Sorry,
think
when
that
yeah, you'll be outputting 0 when majority of yi are 1, and then you can use the same analysis.
yes. So
Right. Yeah.
in calculation, most of the places where we wrote 2 by third here, I mean, we can replace it by 1/3 kind of something.
That would also work. Yeah, probably.
Yes.
Yeah. Okay, so the case when is similar. So A is equal to, let's say, 48n. Running time is at most 48 times n times pn, which is poly-n, and uh, and like 1 minus e to the minus n is a very large number. It's very close to 1, right?
Yes.
Yeah. So we have boosted the success probability of two-sided error algorithms as well. Yeah. Okay, so now, so over in this, like in this lecture, as in, okay, in lecture 2, as I have written in this notes, we saw some concentration inequalities. Okay. Now, so now what I wanted to show is a direct application of concentration inequalities, where using them you can come up with a much better algorithm. Okay. So the problem is this: given an array ARR 1 to n, so array of length n, with a guarantee that either at least 60% of the elements are A for some value of A, let's say A is 10, or at most 40% of elements are A. Okay. Then what's the running time? So what are the running times of the best deterministic algorithm for this problem and the best randomized algorithm for this problem? Okay.
So the problem statement is not clear. That so we have been given an array with the
Right.
guarantee that either 60% of the elements are A or 40% of the elements are A. What does it mean?
Well, let's say your array had size 100, then you know that either 60 of them are A's or at most 40 of them are A's. It
Oh,
cannot happen that at least it cannot happen that 48 are A's and 52 are not A's.
okay. So there is some confusion in the language. I think that either 60% of the elements are A or at most 40% of the
Right.
elements are A. So either
So
we
this
have
is
maximum 40 number of the elements are A, or
right.
we have 60% of the elements are A, and
Right. So
no number in between, say 41
yeah,
or
no
40.
number in between. Yes.
I see. Yes, yes,
Yeah.
yes.
And you want two things. You want number one, a deterministic algorithm which can decide whether at least 60% are A's or at most 40% are A's,
Mhm.
or a randomized algorithm which can decide whether 60% are A or 40 at most 40% are A. Okay.
Yes, yes, yes. So, yeah. So I'll have to scan through the entire list, and
Yeah.
then I see that whether the 40% of the elements are A or not. In case if the 40% of elements are, so I mean, if I go through the entire list once, then we would be able to solve this for deterministic one,
Easily, right.
easy one.
Yeah. So
And
for deterministic, order n is clear, right? You need to
yes,
go to the entire list.
yes, yes.
Yeah. So for randomized, it's not clear. And yeah, hint is you can do something better.
Okay, okay.
Yeah. And okay, so like towards the end of the course, we would have one problem solving session. And so what I'll do is like in every week, I'll have one or two problems like this. You can think about it offline. And in that session, we would see how to solve, what are the solutions to all of these.
Yes, yes, sure.
Yeah.
That would be really helpful.
Yeah. Okay, so now let's move on to the actual lecture 3, i.e. what we are supposed to do today. Yeah.
Okay.
Oh, so okay. My iPad is running low on battery. Is there any way I can charge over here? And there is no way. So let's hope it lasts 30 more minutes. Yeah. Okay, so yeah, so in the previous lecture, we saw concentration inequalities, equivalence between Las Vegas and Monte Carlo algorithms, and a way to boost the success probability of any Monte Carlo algorithm. And today we'll see randomized quicksort. Okay. Okay, so I don't think we will be able to complete the entire thing, but okay, let's see how much we can do. So before we move on to randomize quicksort, let's just look at the quicksort algorithm, okay?
Yes.
So what does this algorithm do? Its input is an array of length n, say ARR1 to n. And for the sake of simplicity, let's assume that all the elements are distinct, okay?
Yes.
Yeah, this is not required, but yeah, it just would make things simple in the randomized case. And the output, the desired output, is that ARR is sorted in the ascending order. Okay.
Hmm.
Yeah. And what does quicksort do at a very high level?
Yes, so we find the right position of the pivot element and then we break it to sublists, right? And every time, I mean, in every iteration, the pivot element will get positioned at the right location.
Right. Okay. Yeah. So it does exactly what you said. So, but okay, the question is, how do you pick the pivot element?
Yes, so initially in the algorithm, we may assume that the very first element is the pivot element that the algorithm proceeds.
Right. So when you are using a deterministic algorithm, you will have to pick the either the first element as a pivot or the last element as a pivot or something like that, right? A fixed element as a pivot.
Yes, yes, yes.
Right. Okay. So let's say we pick the first element as a pivot. And we say there is this pointer which we set to 1. The meaning of the pointer is this: all elements in between 1 and pointer are less than or equal to the pivot. Okay, so we would maintain this invariant throughout the algorithm.
Yes,
Okay, so initially the invariant is true, right? Because pivot is less than or equal to the pivot,
yes.
right? Then for I in 2 to n, we do the following: we compare ARRI with the pivot.
Mhm.
If ARRI is smaller than the pivot, then we swap ARRI and PTR plus 1 and
Yes,
increase PTR to PTR plus 1. So let's say the PTR was here, then we would swap with this element and move the PTR here. And this is fine because now all the elements up to PTR plus 1 are smaller than the less than or equals to the pivot. So we should increase PTR, right?
yes, yes, yes.
So are these two steps fine?
Yes, yes, yes.
Yeah. Okay. And after we have run through this loop, what do we have? We have ARR1 to PTR, and all of these elements are less than or equal to the pivot. Okay.
Yes, yes, yes.
In fact, ARR2 to ARR PTR are strictly less than the pivot because all elements are distinct.
Yes, yes,
So we would just swap ARR1 and ARR PTR. So earlier pivot was at ARR1, now it's at ARR PTR.
yes, yes,
So everything between 1 and PTR minus 1 is less than the pivot. Everything between PTR plus 1 and n is more than the pivot. And so we
yes,
recursively sort these two lists.
yes, yes,
Right. Yeah. So are you convinced that this algorithm would sort the array in the ascending order?
yes,
Yeah.
yes, yes.
Okay. So this was just a recall of quicksort. Yeah. So now let's look at the issue with quicksort. So what's the running time of quicksort?
So yes, so say there are I number of the elements now in the left, and remaining n minus I minus one would be there in the right. Yeah, PTR minus one, yeah, and then T of n minus PTR minus one.
Yeah.
And then plus some effort is required for the execution of this algorithm for the swapping, etc. And I think for this we would be requiring linear amount of the time.
I think it would be something like this. Yeah. N minus PTR plus 1.
Yes. But then plus linear time would be required to.
Oh, yes. So N minus PTR. Okay. Now, in the worst case, what can happen? So, okay, so I want to upper bound the running time Tn, right? So I need to upper bound this quantity, and this quantity. Okay, this is fixed. Don't need to worry about this. But what can happen is this, right? T of 0. Wait, something's wrong. This should be n minus 1. Okay, I messed this. Wait, 1 to ptr minus 1. The 2 should sum to pt n minus 1. So this should be n minus ptr. What am I doing? Yeah, that was right. Okay. So when is ptr minus 1 0? When ptr is 1. So this n minus ptr is n minus 1, not n minus 0. Yeah. And if you solve this, you would get
Of product of n square.
yeah. This is what you would get, right?
Yes, yes.
Yeah. And what's the worst case example? What's the example in which this would happen?
So when the array is already sorted and the very first
Yeah.
element is a pivot.
So let's say it's 1, 2. Yeah, because in this case, ptr would just be 1, right? Nothing is smaller than 1.
Yes.
Yeah. Yeah. So what should have been the best case is actually the worst case. Because
Yes.
over here, you don't need to do anything, right?
Yes. Yes.
Yeah. Okay. So now, okay, what was the issue over here? We ended up, in some cases, we end up picking the wrong pivot, right? A very bad pivot.
Yes. Yes.
So for example, in this case, if we had picked the last element as the pivot, we would have been done in one shot.
Right.
Okay, so now, so what we'll do is we'll use randomization to uh, pick the pivot. And okay, so, and okay, at a very high level, our hope is this. For any given array, there are only a few bad pivots.
Mm-hmm. Mm-hmm.
And if we pick a pivot randomly, the probability of picking those bad pivots would be small, and so we would be fine.
Okay.
Okay, so here's what randomized quicksort does formally. Uh, its input is an array of n elements. Those elements are distinct, and output is supposed to be an array in the sorted in the ascending order. Okay, and so the algorithm proceeds as follows. It first samples n r uniformly at random from 1 to n, and then it swaps ARR1 and ARR, and then the pivot is ARR1, and then it's the same as the previous algorithm.
Mm-hmm.
So what this is doing is it's picking a random index, saying that the value of that index is going to be my pivot,
Yes. Yes.
right? And I'm only swapping that value with 1 because I want to use the previous algorithm.
Yes. And in
Right.
every iteration of this procedure, every time we will be selecting a different value. I mean, since different
Right.
value of R.
Yeah. So now we are recursively calling randomized quicksort, right? Not deterministic quicksort.
Yes. Yes.
So in every one of these, it would again pick a random pivot and proceed, right?
Mm-hmm. Right.
Okay. So is the algorithm clear?
Yes, algorithm is clear.
Okay. So here's a question. This algorithm is randomized.
Mm-hmm.
So can it ever make a mistake? That is, can it ever give a solution which is wrong?
So, because even though we are randomly selecting the pivot element, so the essence the algorithm is like that every time all other elements will be smaller than the selected pivot element on the one side,
Right.
and on the other side the elements which are greater than the pivot element. So this
Yes.
algorithm as such is not going to make any mistake.
Right. So this algorithm can never make a mistake, right?
Yes, yes.
Okay. So the claim is this. Okay, so this already looks something like what?
So this is like Las Vegas kind of thing.
Right. The only thing that we have to prove is that the running time is something in expectation, right?
Expected running time is called down.
Yeah. So we already know that the expected value of running time is at most n squared,
Yes.
right? Because even in the deterministic case, it was n squared.
Uh, yes. Yes. But then this we can get this n square value say multiple times, quite possible. Not n square as such, but then so quite possible that we may end up I mean that split multiple times. But that won't make any impact because the average case complexity of the quicksort is also of the order of n log n only.
Yes, that's what we'll prove. So
Okay.
that's what the theorem says. But what I'm saying right now is that, uh, yeah, just given this algorithm, we can say that its running time would be at most n square, even in expectation. It won't do worse than that.
Yes, yes, that's true.
Yeah. But now we would prove something much better. We would show that the expected running time of randomized quicksort is order n log n.
Okay, okay.
Yeah. Okay, so let's see how. So let AI denote the ith smallest element in the array. Okay.
Yes.
So the sorted array looks like A1, A2 up to AN.
Hmm. Hmm.
But in ARR, these AIs are in some arbitrary order, right?
But in I could not hear this thing properly. But
In ARR, these elements A1, A2 up to AN can be in some arbitrary order. For example, it could be AN, A2, A4, A5, A6, A1, right?
yes, yes,
Yeah. Okay. And okay, so the running time of quicksort is dominated by comparisons, right?
yes,
So the only things we are doing are comparisons and swaps happen after comparison.
yes.
Yeah, so the running time is dominated by comparisons. In fact, in particular, it's like almost 2 times the number of comparisons.
Mhm.
So I can just upper bound the number of comparisons, right? So if I were to show that number of comparisons is order n log n, I would be done,
Yes.
right? Yeah. So since the running time of the quicksort algorithm is dominated by the number of comparisons, we will just show that in expectation, the number of comparisons is order n log n. Okay.
Okay. Okay.
Yeah. Okay. So for now, for all I in n and j greater than I, let's define this random variable. So this random variable is 1 if AI and AJ are compared and 0 otherwise. Okay. So we want to determine the number of comparisons. Now in comparisons, at least 2 elements are involved, right?
Mhm.
So there are at most n order n square many possibilities of pairs. For
Mhm.
every such possibility, I'm defining a random variable, which is
Mhm.
1 if they are ever compared in the execution, 0 if
Mhm.
they are never compared in the execution. Okay.
Yes.
Okay, so given these xij's, the question is, what's the expected number of comparisons? Can you write this in terms of xij's?
Okay. So every number of the comparisons would be say I varies from so I and j. So I varies from 1 to n, j varies from 1 to n, and yeah. So the summation of the entire thing and then
Yeah,
divided by value n.
right. So this is yeah, j equals to I plus 1 to n because j is greater than equals to I. That's the only case when AI xij is defined, right?
Yes, yes, yes.
And what's this?
So I mean, this is the comparison. So therefore, we need to add these things.
Yeah, so like what I meant was I can write this as
Oh, yeah,
something.
and yeah,
Yeah,
I can, yeah, this summation outside this thing, and then expected value of the xij,
right.
and summation will come out linearity of the expectation.
Yes. Okay. So if I were to find expected value of xij for all of them, I would be done, right?
Yes.
Okay. So now what we would do is the following. So you can think of the execution of quicksort as sort of creating a binary tree, right?
Mhm.
Let me call this tree T and define it as follows. So the root of tree is the pivot
Mhm.
picked in the first recursive call to quicksort, right?
Yes.
The elements in the left subtree are going to be all the elements less than the pivot. Elements in the right subtree are all the elements more than the pivot.
Yes.
Okay. Okay, so I wanted to construct a tree. So far, I only constructed it partially, right? I have said that okay, there is this root. It has a left subtree. It has a right subtree. I have told you what this is, but I haven't. I only told you what these elements are, but I haven't shown you how how they are like arranged as a tree, right?
Yes.
Okay, so how would I arrange them as a tree? Well, on all the elements in the left subtree, I'm going to recursively call quicksort.
Yes.
So I would do the same thing again. That recursive call to randomize quicksort would pick a pivot, again divide the array into two parts,
Mhm.
right? So for the left subtree, the root would be the pivot picked in that recursive call. The nodes in the left subtree would be nodes smaller than that pivot, and the nodes in the right subtree would be the nodes would be the numbers more than the pivot. Okay,
Yes.
so I can recursively define the tree using the pivots picked by the various recursive calls of the two randomized quicksort, right?
Yes. Somewhat similar to the binary search tree kind of the thing, wherein the left thing is smaller and the right thing is greater kind of.
Yeah, so this is essentially a binary search tree. In fact, I think you can even show this is a random binary search tree.
Okay.
Yeah. Okay. Yeah. Okay. So let me just read over this once in case I missed something. So construct a binary tree as follows. A binary tree T as follows. Its root is the pivot. The left subtree contains elements in ARR 1 to PTR minus 1, and the right subtree contains elements in ARR PTR plus 1 to n. The root of the left subtree is the pivot picked when randomized quicksort was recursively called on ARR 1 to PTR minus 1, and similarly for the right subtree, right? And then we define this recursively.
Yes.
Okay, so now let pi be the level order traversal of T. So what does this mean? I first look at the root, then I look at its children, then their children, and so on, right?
Okay, so what kind of traversal would it be? Say, first I would be so in what I mean different type of traversal. So I mean level order. Okay.
The level order. So okay, that's a good question. So this is a level order traversal, but would have gotten this traversal if I had used some. Okay, so what are the a tree is a graph, and what are the two algorithms that we know to traverse a graph?
BFS, DFS.
Right. And question is this: would I get this traversal if I were to use one of those two?
Yes, so we can go for the BFS thing wherein we conduct the
Yeah.
search little by little.
BFS with what? With the first element being the root, right?
Yes, yes, yes.
Yeah. Then yeah. Okay. Not exactly because in level order traversal you go from left to right.
Mm-hmm. Mm-hmm.
So in BFS you just need to make sure that okay, the root has two neighbors, the left one, the right one. You pick the left one first. That's the only thing you need to worry about.
Yes,
Yeah. So that because that's how I have defined pi. But yeah, it's essentially the BFS.
yes.
Okay. So now our proof would just rely on two observations. Okay. My battery is low. Okay, it will last for 4 minutes. Fine. Okay, so my claim is pi is a permutation from A1 to n to A1 to n. Why?
Yes, so because this is level by level traversal.
Right.
So
Okay, so basically, whenever I pick up pivot, that pivot would appear in pi, and then the pivot never appears in the lower levels, right?
Yes.
So one element never occurs twice in pi,
Yes.
and pi has all the n elements,
Mhm.
which means every element must occur exactly once,
Yes.
because it occurs at most once and all are present,
Mhm.
right? So it every element in pi occurs, every element in A1 to AN occurs in pi exactly once. Therefore, it has to be a permutation of A1 to AN, right?
Yes. Yes.
Yeah. And the second observation is Xij is 1 if and only if I or j appears in pi before any other element in AI to AJ. Okay.
What does it mean? That we are comparing I and J.
Hmm.
If what the sequence here signifies that AI.
Okay. So the right part of the sentence means the following. So okay, look at pi. The first element of pi is the first pivot that I picked, right? The
Yes.
second element of pi is a pivot that I picked when I made recursive call to the left subtree. Uh, the second element is the pivot I picked when I made recursive call to the right subtree, and so on, right?
Yes.
So
Yes.
basically, the first element is the first pivot I picked. The second two elements are the next two pivots I picked, the next four pivots I picked, and so on.
Yes. Yes.
Okay. So what I'm saying is I or j appears in pi before any other element in AI to AJ, which means that I picked AI or AJ as pivot before any other element in AI to AJ. Okay.
Mhm. 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 It's not
Yeah.
that much clear probably. Yeah, but then I'll ponder upon this.
Yeah. Okay.
So,
So actually, it would become more clear. Okay. So this statement is sort of unclear. Okay, let me do this. Suppose that till now I have never picked an element in AI to AJ as pivot. Okay.
yes.
Then my question is, can AI to AJ be split into different trees till now? So I have done some recursion. I have constructed the tree T partially, okay?
Mhm. Mhm.
Because till now I have only picked some pivots.
Mhm. Mhm.
So
Mhm.
far I have not picked any element in AI to AJ as pivot. And the
Yes.
question is, can AI to AJ be split into two different subtrees?
No, 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 no.
Why?
No, no, cannot be because I mean only the elements prior to AIs have been selected as the pivot elements.
Right. So either okay, what are the pivots that we have selected so far? Either elements before AI or elements after AJ, right?
Yes, yes, yes,
Now,
yes.
whenever you pick a pivot which is before AJ, AI, all these elements would appear in the right subtree.
Yes,
If you pick something after AJ, they would appear in the left subtree.
yes, yes,
So
right.
these always occur together till you pick a pivot between AI to AJ, right?
Yes.
So what I'm saying is this. Uh, till some point, I have not picked anything between AI to AJ. So all of them are in one subtree. Then there comes a time when these are split into two subtrees, right? Because they have to be sorted.
Mhm. Mhm.
So that happens when I pick some element in AI to AJ for as a pivot for the first time.
Mhm. Mhm.
So what I am saying over here is the following. The first element between AI to AJ picked as a pivot is either I or J.
Yes.
Yeah.
Yes.
So that's what this sentence is saying. So what the observation is saying is this: Xij equals 1 if and only if the first element picked as pivot between AI to AJ is either AI or AJ. That's it.
Right. Right.
Okay.
Yes. Yes.
So is this fine?
Yes. Yes. Absolutely.
Yeah. Okay. So we are out of time, and I still need to prove quite a bit few things. Okay. So let's continue from here tomorrow. Okay.
Sure. Sure.
So tomorrow, what I'll do is I'll quickly, like, again recall quicksort, randomize quicksort, and the definition of these random variables, and quickly go over this tree construction. Okay.
Sure. Sure.
Yeah. So then we will we won't talk about observation 1. We'll just move to observation 2 and we'll prove it.
Sure.
Okay, so tomorrow we are meeting at the usual time, 5 to 6:30.
Sure.
Yeah.
Absolutely.
That's fine, right?
Yes.
Yeah. And like one more thing, have you gotten an email from ISSS giving you the credentials to the course page?
Yes, I got, and I joined that. That link, eGrew. I joined, but then
Okay, so like what did you join?
yes, so it shows eGrew. eGrew is the name of the platform. After
Oh,
after
okay. Yeah.
after
Yeah.
signing login credentials. So, but then on that portal, notes are. I mean, nothing is available as such.
Yeah, so I haven't uploaded anything yet.
Yes.
I'll upload it either today or tomorrow.
Sure.
Yeah. Okay.
Yeah. No issues.
Yeah.
Either you send these notes to the email or you upload there. I mean, is what I mean, is okay. Absolutely fine. No issues.
Okay, so okay, today at least let me share whatever we have done today with as an email.
Yes.
Yeah, because I'm not sure I'll get time to upload it today because like I have 3 videos and all of these are large. So I either need to compress them. Like okay, the problem is it only lets me upload videos up till a limit. I think it's 500 MBs.
Okay.
And some of these 3 videos are large. So I either need to compress them or find or like upload them on my Google Drive and then upload a link.
Okay. So you
So I need to
please,
check with
please
them if this uploading link business is fine.
yes. So you
Yeah.
please notes through email today, and
Yeah. Okay.
later we can use the portal.
Yeah.
Sure. Thank you so much.
Yeah.
Good to know.
Thanks. See you tomorrow. Bye.